This is part 13 in our series of lectures on infinite sets. In this lecture, I'm going to show you a proof of the Cantor-Schroder-Bernstein theorem. Recall the theorem says that if we give ourselves sets A and B, and if there exists an injection from A to B and an injection from B to A, then there necessarily exists a bijection from A to B. So in order to do the proof, I'm going to begin by giving you a few genealogical definitions. For each x in A and each y in B, we're going to define the set of descendants of x and y. So let's start with x. The set of descendants of x are what? We start with x, then we know that f maps from A to B, so that means it makes sense for us to take f of x. That gives us an element of B. Then I can take g of the result. That will then bring us back to A, so I can take f of that result, etc. We just keep taking the image of the resulting elements, and we call those the descendants of x. And similarly, we get the descendants of y by starting with the image of y under G and continuing with the same pattern. So any element of this set D sub x is referred to as a descendant of x, and any element of this set D sub y is referred to as a descendant of y. So this element here is a descendant of x, this element here is a descendant of y. So that means we can take descendants of any element in A union B. And so if we give ourselves any two elements in A union B, we say that Z is an ancestor of W, provided W is a descendant of Z. So for example, this element here is an ancestor of this element here. Of course, every element, according to this definition, every element is an ancestor and a descendant of itself. We're going to find it useful to illustrate what these things look like by means of graphs. And by graph, I don't mean the kind of graph you see in a calculus course, but rather the kind of graph you see in a discrete math course. So for x in A and y in B, we can draw some of the descendants of x and y by a directed graph. So here's the directed graph that shows some of the descendants of x. Here's x. The arrow indicates that we're taking f of x, then we take g of f of x, then we take f of g of f of x, etc. And similarly, we can illustrate some of the descendants of y with this graph. So in the graph, the vertices of the graph, in other words, these points, represent elements of A union B, and the arrow indicates how we get from one vertex to another, from one point of A union B to another, by means of either taking f of it or g of it. If you happen to find yourself in A, as you do here, then you have to take f of it to get there. Now you're in B, so you take g of it to get there, etc. Now, is it possible that the ancestors of x and y can look like this? So I've drawn x here, and these two represent ancestors of x, so they because clearly x is a descendant of each of them. Is it possible that it looks like this? Well, the answer is no. They can't look like that, because if we had a vertex that looked like this, then it would be the image of two different things, and that would contradict the injectivity of f and g. So they can't look like that, and that means that the only way they can look is something like this. They must, if this is x, then they would all have to come from the same straight line. There's no branching possible for ancestors. So that allows us to deduce this fact here, that if Z1, Z2, and W are three elements of the union, if Z1 and Z2 are ancestors of W, so here think of this one as being W, think of this as being Z1 and Z2, it's saying that the picture can't look like this. The Z1 must either be an ancestor of Z2 or Z2 must be an ancestor of Z1. It must be along a single straight line. So now we define a relation R on A union B as follows. If X and Y are in A union B, we say that X is related to Y, provided X is either an ancestor of Y or Y is an ancestor of X. Then I claim that this R is actually an equivalence relation on A union B. The reflexivity and symmetry are completely obvious. Everything is related to itself because everything is a descendant of itself. And symmetry is built right into this definition here. The tricky one is the transitivity, but that follows from the comment I made on the previous slide, which says that if Z1 and Z2 are both ancestors of W, then either Z1 is an ancestor of Z2 or Z2 is an ancestor of Z1. That's exactly what you need in order to prove transitivity. Well, the moment you have an equivalence relation on a set, then you automatically get the result of the equivalence class theorem, which says that the underlying set, A union B, is partitioned by the distinct equivalence classes. And as we'll see, there are exactly 4 different types of equivalence classes. I'm going to show you a sketch of what they look like, and depending upon what they look like, our function h, this thing that we're going to try to define as a bijection from A to B, the value of h of x is going to depend upon which of the types of equivalence classes x lies in. Okay, this is what all of the various equivalence classes can look like. The first one looks like this. So the implication here is that every element in this equivalence class has infinitely many ancestors. This goes back forever, and infinitely many descendants. The other possibility is that it cycles back on itself. It's quite possible when you keep taking images of the various elements as you move back and forth between A and B that you actually come back where you started from. So you might start in A, then you map to B, then G maps you back to A, then F maps you back to B, and then G maps you back to where you started. But you'll notice in such a situation that there's always going to be an even number of edges in such a thing because it takes you an even number of steps to go from an element of A and to return to an element of A. Now what about types 3 and 4? We're assuming that F and G are both injective. If either one of those were actually surjective, well then there wouldn't be anything left to prove. Then we would have our bijection between A and B. And therefore we have to assume that neither F nor G is surjective. And therefore there have to exist vertices in A which aren't the image of anything coming from B, and so that's what I've illustrated here. You can't go backwards any more than this one. And there have to exist vertices in B for which it isn't the image of anything in A. So that gives rise to types 3 and 4. So now finally I'm ready to tell you what is this function h of x. So to do that I'm going to locate an x on each one of these equivalence classes, and then I'm going to show you in the picture how we're going to define h of x. Here's the answer. If x lies in an equivalence class of type 1, then we're going to map h of x here. In other words, we just take f of it. If x lies in an equivalence class of type 2, once again I'm going to take f of it. This is going to be my h of x here. See, I'm just going on the forward direction of the arrow. And similarly, if you're in type 3, I'm going to map h of x to this vertex here. And that will work because even if my x is over here, that's an element of A, my h of x would be there. Now the tricky one is type 4, because you see this element here isn't the image of anything, it isn't the forward image of any element of A. So what we're going to do is we're going to reverse the direction. If x is in this equivalence class, the h of x is going to obtain by going backwards. And that means if my x is here, my h of x would be there. Okay? So I think you'll see it's very easy to convince yourself that with this assignment of h of x for any x in the for any x in A, the h of x gives us a unique element. It's injective, but it's also surjective because you see any y value is also in one of these equivalence classes. If y happens to be here, then it's the image of that. If y happens to be, say, here, then it's the image of that. If y, say, is here, then it's the image of that. And if y is anywhere along here, say here, then it's the image of that. That completes the proof.